All right, so we've talked about Coulomb's law. We've pointed out that like any force, the electric force is a vector, and so if you want to think about the electric force on a single charge in the presence of multiple other charges, we need to work a vector addition problem. So as an example, here we have a situation where we have three charges fixed in the xy plane. Particle 1 carries a charge of -2 nanocoulombs and lies at the origin. So here's particle 1 in our picture. Particle 2 carries a charge of +5 nanocoulombs and lies along the positive x-axis 4 meters away from the origin. So here's particle 2. Particle 3 carries a charge of -8 nanocoulombs and lies 3 meters directly below particle 2. So we came 4 meters out, 3 meters down. So here's particle 3. We're interested in what's the magnitude and direction of the net electric force exerted on particle 1 by the other two particles. And so the first thing we need to make sure that we're very clear about is what's the charge that we want the net force on. Right? So there are multiple interactions, electrical interactions going on here. There's an interaction between charge 1 and 2. There's an interaction between charges 2 and 3. There's an interaction between charges 1 and 3. If we want to calculate the net electric force on particle 1, then we only want to think about the forces that charge 1 feels, not any that charge 1 causes, and not any that take place between two other charges. So that's a detail that we need to make sure that we are very clear about up front. Otherwise, we're going to be adding together the wrong vectors. The second thing we'll go ahead and do is go ahead and take care of labeling whether the charges are positive or negative. So again, charge 1 was negative, charge 2 was positive, charge 3 was negative. We're going to go ahead and put that straight onto our picture to help us keep track of things. And then we'll come back and again take care of some of the geometry that we know that we're going to need. So if I'm interested in the forces on charge 1, then I know I'm going to need to know the distance from charge 1 to charge 2 and the distance from charge 1 to charge 3. So the distance from charge 1 to charge 2, that's R12, that's 4 meters. We were told that in the problem statement. The distance between 1 and 3, well, if it's 4 meters to the right and 3 meters down, again, I Pythagorized those two distances, and the square root of 3 squared plus 4 squared says the distance between particles 1 and 3 is 5 meters. Okay? I also know that the forces charge 1 feels are going to lie along those lines that I've drawn out there in red. And so that means that there's going to be an angle that I need to go ahead and calculate because it's going to matter. And so I'll define theta to be the angle between the line between charges 1 and 3 and the x-axis. And so again, then I can use my inverse tangent function to get that theta is the inverse tangent of opposite side of 3 meters, adjacent side of 4 meters, and so I get that theta happens to be 36.9 degrees. So all these are just some values that we're going to end up needing as we go ahead and do our calculations. All right, so the next thing we need to do, so let's go ahead and draw the free body diagram for particle 1. So what are the forces exerted on particle 1 by the other two particles? So for starters, if I think about the interaction between particle 1 and particle 2, one of those is positively charged, the other one is negatively charged. I know that opposite charges attract, which means that charge 2 is going to pull charge 1 to the right, so I can draw in that force. So initially I'm going to go ahead and label these with sort of my full labeling as the electric force on particle 1 by charge 2. Okay? When I look at the interaction between 1 and 3, well, they're both negatively charged. I know that like charges repel, which means that particle 3 is going to push particle 1 away from it. So there will be a force exerted on particle 1 by charge 3 that points up and to the left. I can come back and draw my coordinate system on top of my free body diagram. And again, I see here that there's this same angle theta. Right, so between the line that connects charges 1 and 3 and the x-axis, so this must be theta again. And so now I've got a coordinate system, so I can break these vectors up into components. So I know that I'm going to be setting up two component equations to do the vector addition. So I'll go ahead and set up a table to help me keep track of the vector components for each of these vectors. The other thing I'll do is just simplify my labeling a little bit. So again, the electric force on charge 1 by charge 2, I'm just going to relabel as F2. The electric force on charge 1 by charge 3, I'm just going to relabel F3. So now F2 is the magnitude of the force between charges 1 and 2, and F3 is the magnitude of the force between charges 1 and 3. I see that the force exerted on particle 1 by particle 2 points to the right, which means its y component is 0, its x component is positive, and the entire magnitude is in the x component. The force between 1 and 3, that points up and to the left. So the up says positive y component, to the left says negative x component, given my choice of coordinate system. Again, I see that theta makes an angle with the x-axis. So the x component's going to need the cosine theta, the y component's going to need the sine theta. And again, there's the magnitude of that force in both those components. I don't know anything about the net electric force, so as I usually choose to do, I'm leaving it as components to go ahead and set up my equation. So in this case, I got two equations, one that tells me that the x component of force 2 plus the x component of force 3 equals the x component of the net electric force. My y component equation says the y component of force 2 plus the y component of force 3 equals the y component of the net electric force. So using the components that we've set up in the table, I've got one column here to give me my x equation, the other column to give me my y equation, and so here are my two component equations all set up. I know theta. My two unknowns are the x and y components of the net force. The next thing I need to do then is go calculate what are the magnitudes of F2 and F3 so I can plug those into my equations. So to calculate the magnitudes of my electric forces, I know I'm going to use my Coulomb's law equation. So K Q1 Q2 over R12 squared for the magnitude of the force that between particles 1 and 2. K, I know what that is. That's the 8.99 times 10 to the 9th. Again, I've got the absolute value around my two charges, so I drop the minus sign for Q1. There's Q1, there's Q2. They're nanocoulombs, so I need to get my unit conversion right. And the distance between them is 4 meters, so that 4 ends up getting squared in the bottom. And I calculate that the magnitude of the force between charges 1 and 2 is 5.62 times 10 to the minus 9 newtons. Do the same thing for the force exerted between charges 1 and 3. So F3 is K Q1 Q3, both in absolute values again, over R13 squared. K still the same, 8.99 times 10 to the 9th. Q1's the same, again with absolute values, so no minus sign. Q3, plug that in, again absolute values, no minus sign. The distance, we calculated right up front that the distance between charge 1 and charge 3 is 5 meters. So I plug in that distance, it gets squared, calculate that out, and I get that the magnitude of F3 is 5.75 times 10 to the minus 9 newtons. Now I can go plug those two magnitudes into my component equations. So they're my component equations. There's x, there's y. Plug in F2 and F3. I'm only left with the x and y components of the net force as my two unknowns. Each equation has its own, or each unknown has its own equation. So I can go ahead and use my x equation to solve for the x component of the net electric force. It's 1.02 times 10 to the minus 9 newtons. Use the y equation to solve for the y component of the net electric force. It's 3.45 times 10 to the minus 9 newtons. So here I've got the x and y components of the electric force. So one way that I can report what the net electric force exerted on charge 1 by the other two charges is just give it in unit vector notation. So in this case, x component I hat plus y component j hat. So 3.45 times 10 to the minus 9 newtons I hat plus 1.02 times 10 to the minus 9 newtons j hat. Of course, if I know the components, I might be interested in magnitude and direction. So to get the magnitude of the net electric force, I want to Pythagorize my x and y components. I'll do that. Again, I've chosen to just deal with the 10 to the minus 9 outside that. And I get that the magnitude of the net electric force is 3.6 times 10 to the minus 9 newtons, 3.6 nanonewtons if you like. And its direction, again, I can use the inverse tangent. So here I've defined the angle phi to be the angle between the net electric force in the x-axis. And so I see that because I've got two positive components, I'm going to have an angle that's above the positive x-axis. Plug in my y component over x component, do the calculation, I get 73.6 degrees above the positive x-axis. So this is the process that we'll get very comfortable with, because we'll work plenty of problems where we're calculating the net electric force on one point charge due to other point charges in its vicinity.